So before we start this problem, let's talk about work done by a spring in general. And I've underlined the by because it's important which point of view for work, who you're looking at, because that's going to determine whether the work should be positive or negative. Is the energy flowing in or is the energy flowing out? But it's going to be work done by a spring. And before we do that, let's go back and remind ourselves about spring forces. So you got a little spring. There it is. Let's attach one end to a wall or something. So that is what I have done to just draw a wall, something that is fixed and won't move. We'll stick a little mass here so the force can do work on this little mass. The spring can do work on it. And how springs work is they have a length that they like to be. They have an equilibrium length. And that is the length where the net force on this little spring is 0. So equilibrium, remember that means the net forces, all the forces, they sum up to 0. So this is the equilibrium length. I'm going to call the position that the spring, the end of the spring is at. I'm going to call that x sub e, e for equilibrium. So that will be the equilibrium position. And if we take our spring and then it's, at its equilibrium length at some moment, if we stretch it out, so now the mass is over here, and now that's the end of the spring, and draw it down, we have displaced the spring over here to some new position x. And the displacement, the stretch of the string, is that new position x minus the equilibrium position. And if we do this, the force of the spring is going to be back towards its equilibrium position. So the force of the spring will be this way, trying to get it back home, back to its normal happy length. And if we squash the spring instead, so instead of stretching it out, we have squished it in like this instead and moved the mass here, well, the spring is still not happy. It wants to be at its equilibrium length, not longer and not shorter. So now we have displaced the spring that way. So it's its new position minus the equilibrium position, and the force is trying to get it back to equilibrium. So the force is going to be back that way now. And we write all of this in the equation for the spring force. So if we do it as a vector, then it is negative the spring constant k times where the end of the spring is minus its equilibrium position. So where it is minus where it wants to be. So that's the spring constant, which is a property of an individual spring, basically how stiff it is. And this negative, that's the thing that's symbolizing when you displace it this way, going off that way, the force is the other way. When you displace it in this way, the force is back the other way. So the force is always opposite this displacement. So there's a negative sign to multiply this displacement to say that the force is in the other direction. So that is perhaps the most important bit of modeling the spring. The force is always opposite the spring's displacement, always in the opposite direction. So knowing that, we are now ready to figure out what's the work done by this spring force. Well, like any other work, it is a path integral from where you were initially, your initial x position, to your final x position, and it is the path integral of the force, which in this case is the spring force, and the dot product of that force with the displacement. I'm going to call the displacement x here because, that's what I've called it in the spring force. So the dot product, to remind ourselves, nothing happens with the integral because we're just dealing with the dot product right now. So x initial, x final. The dot product is the magnitude of the two vectors, so the magnitude of the spring force, the magnitude of the tiny little infinitesimal step, and then the cosine of the angle in between them. All right, so the magnitude of the spring force, well, it's going to be this. But just to make our life a little bit easier, I'm going to use the convention that most people use. In general, most people make their origin the equilibrium length of the spring. So that is right here. We'll make this the origin. So in other words, we'll set that equal to 0. So if we do that, then the force of the spring is negative k times however you have moved away from that displacement. And the magnitude, and I'm just going to write in xi for the initial and xf for the final position. The magnitude is the absolute value of this. So just the spring constant times x. That's the magnitude of the spring force. The magnitude of this infinitesimally small step is just dx, and the cosine of the angle between them, well, that, because the force is always opposite the direction the spring is displaced, this angle is always going to be 180 degrees. That is always going to be true. And therefore, the cosine of 180 degrees, well, that is equal to -1. So when we do the work, we will get the integral from the initial position to the final position. Get a -1 here, kx dx, so just writing those down, times -1. We can move everything that is not a variable, not having x in it, outside. So the -1 will come out, the k will come out. We'll be left inside with x times dx. And we're doing the integral, so the power of the thing we're doing the integral of is going to increase. So we went from x to the 1, we're going to go to x to the 2. So keep writing our -k, do the integral. This was x to the first power. We do an integral, we increase it. It'll be x squared. We have to divide by that power, so divide by 2. And then we have to evaluate it at our integration limits. So the initial x position and the final x position, we'll rewrite this, it'll be negative. I'm going to move that 1/2 out in front, k, and then we'll plug in the x final. X final squared, and then we have to subtract off the x initial. There we go, and that is going to be the work done by a spring. So let's take a look at this now and just sort of double check that it makes sense. So if we start at the equilibrium position, so that means our x initial is that x equilibrium, which we've said is 0, because we've set it equal to the origin. And we pull it to stretch the spring. So that means we're doing this kind of thing. We're pulling it that way. What do we get for the work? Well, we get -1/2. The spring constant, always going to be positive there. Whatever our final position is, it'll be somewhere over here, minus our initial position, but our initial position is 0. So 0 squared, that means we're going to get -1/2 kx final squared. So our work is negative. Does that make sense? Well, we started here and we moved that way. But the force from the spring was always opposing us. So we were displacing this way. That was our displacement. And the force was in the opposite direction from the spring. So that makes sense. We should get a negative work, and then thinking about energy, well, if we're displacing this way, the spring force is always working against us, making it hard as we pull that little mass out. So yeah, the spring force is stealing energy away from us. So it does make sense that that work should be negative. So this is how work is done by a spring force. That's the general formula. Where you end up squared minus where you started squared, and then a negative 1/2 k out in front of that. And here's kind of how you would plug in. Plug in our starting position. I didn't give you a number for the final position, but then you can double check. Does the sign make sense with what's going on, with how the displacement's working and how the force is working? Now let's go ahead and apply this to a particular problem.